Hello everyone and welcome back. So in this tutorial we are going to talk about a stack. Now, what is a stack? So let me explain what a stack is. A stack is simply a data structure. A data structure. So what you would do, you could have, let's say, in plates. If you're stacking up plates, you would have the first plate, the second plate, let's say that, the third plate, you can have the fourth plate, and so on and so forth. Now in a stack, it is that in a stack it's that the last element you add, or the last plate you add, it will be the first plate to get out. So it works in the principle of last in, first out, meaning that the last one, the last that you add is the first. It's the first that leaves. That's the principle that it works with. So to do that, to code a stack, we shall need to create a new file. So we're coding a stack in Python. We shall have to create a new file. So after creating the new file, let's save it somewhere, and you can save it as stack.py. So what do we need? We need a node. So we need to create code the node. So we shall say class node. Then a node needs to have the data. It needs to store a data, needs to point to the next node. So we shall set define, shall initialize our class with self, then it passes in data. Then from there we shall say let our self dot data equal to data, and let our self dot next, it's going to be the next pointing to the next node. Let our self dot next equal to none for now. Then we are going to define our class of a stack. So our stack will need some functions. So we will need a function to check if the stack is empty. Take in self, then I'm going to say pass. It will need a pick function to just return for me the data of the last element to enter into the stack. So I'll just say self, then I'll pass. Then we need another function to add information onto the stack. So I'll say define add, then I'm going to pass in self, then the data that we need to add, then I'll say pass. Then we need another function to remove information from the stack. So I'll say remove. So remember, when you remove information from a stack, you need to delete the top node, meaning that the last node to enter is the one where you remove the information from, and then you need to delete it from the stack. So I'll say pass. So now, what do we need to keep track of in a stack? So in a stack, since you are stacking up, let's say nodes, the first node, second node, third node. So this may be the first node, second node, third node, fourth node. So all we need to keep track of is this top node. That's the only thing we need to keep track. This is called the top node, and this could be called the head node. But all we need to keep track of the top node, because the top node is whereby from the top node we can add new information onto the top node, and then from the top node is where you can remove information from. So all we need to keep track of is the top node. So to keep track of the top node, we shall have to first initialize our stack function. To do so, we shall call def init, then we shall say self, then we shall after calling self, then we shall say self.top should equal to none initially. So to check if the stack is empty, we shall just check if self.top is equal to none, then it is empty. So if it is empty, then we shall maybe do something. Let's say print. I can print empty. can print is empty. So now pick. So to pick, meaning that just look into the stack. What is it? Data. That's the data from the top element onto the stack. So to do so, you can just return self.top.data. So then, what if we wanted to add information onto the stack? So then we shall come, then you pass in the data, then we shall create our new node, which will equal to node, then we pass in the data. Then from there we shall check if self.top is equal to none, self.top is equal to none, then our self.top will equal to the new node, then we return, meaning that we end there. What if self.top is not equal to none? So if self.top is not equal to none, what we shall do, we shall select self.top.next equal to the new node. Then now we need to now set our top node. Our top node is now the new node. So we shall say our self.top will equal to new node. So that's how you add information onto a stack. What if we wanted to remove information? So then we shall just select data equal to none. Then we shall say, if data is equal to none, we shall say if self.top is not equal to, if self.top is not equal to none, because if self.top is equal to none, there is no information on this stack, so there is no data to be retrieved. But if self.top is equal to none, what should I select? Data equal to self.top.data. Then we shall select self.top equal to self.top.next, meaning that now since we have removed data from the top node, now we need to set the top node to be the what? The next node. So our self.top will equal to our self.top.next. Then from there, what we shall do, from there we shall return our data. Probably, yeah, yes. Then from there we shall return our data. So that's how you make. That's how you make a what? That's how you make a stack. Thank you for watching. If you enjoyed this video, please leave a like, leave a comment, subscribe to the channel. Thank you again for watching. So hello everyone and welcome back. So in this video we are going to talk about a queue. Now my question is, what is a queue? So a queue is simply a data structure. Let me delete that. So a queue works in this case. If we have let's say a line of people, this is the first person, second person, third person, the fourth person, the fifth person, and they are moving somewhere, like they are going somewhere, like into a movie theater. Now the first person to arrive, or the first person in that queue, will be the first to be served. So this person will be the first to be served. So if they like the man at the movie center says next, the person who will come is this person. The person who will come will be this person, this first person. He will be the one to come. He will be taken out of the queue. So that's how a queue works. A queue works with the principle of first in, first out. That's the principle that a queue works in. First in, first out, meaning that the first to come is the first to be served. So how shall we code a queue? So first we shall need a class, node class. So we shall create a new file, then save it as q.py. That is the file. Save it as q.py. So let's continue going. q.py. So then we need to create a node. So when you create our node, what our node should be able to do, it should be able to store some data. So if I initialize my class, call in myself, then pass in data, meaning that the data will be passed into the node. Now the node should be able to store data. So to do that, I will say self.data will equal to data. Again, the node should be able to point to the next node. So self.next will equal to none initially. So that is points to the next node. Then I'm going to call start developing my class called Q. So when I'm developing my class called Q, I need some there are some initial functions. So you can develop as many functions as you want depending on the characteristics of the functionality you are trying to achieve. So what I can do, I can define a function which checks if the queue is empty. So I'll say is empty, passes text in self, let me say pass. Then I'm going to define another function called pick. Now what pick does, it just returns for me the value of the current value which you are supposed to return. That is the head value or the tail value in this case. I will explain what it's the tail value, not the head value, so I'll explain it later. Self.data. Now let me say pass. No, so it's not supposed to be the add, it's supposed to be the pick. Sorry for that. So I will define I will define my function pick. After defining my function pick, it will take in of course self, then I will pass. Then again I need to put the add function. Now the add function just adds data onto the queue. Then after that I'll put the remove function. So I'll define remove. So what the remove function does, the remove function simply just removes my information from the queue. So now let's first go back to Paint and see. So if this is my queue, to add information, I need to, when you add a new node comes to the queue or a new person comes to the queue, he enters from behind, right? Enters from behind. When I want when the person in the movie theater calls the next person, he comes from the front. So that's how it works. So in this case, we shall need to keep track of the tail value, which is this one. In this case, we shall have to keep track of this value, which is the tail value. We shall also have to keep track of this value, which is the head value. So we need to keep track of both of them. So remember, all of them are linked. They are linked, or they point to each other. This points to that, that points to that, this points to this, and that points to that. So we need to keep track of the head value and the tail value. To do so, to keep track of the head value and the tail value, we shall need to initialize our queue function. So when I initialize it, it will take in self. Then I'm going to say self.head will equal to none. Then self.tail will equal to none. So that's how I have initialized. I've initialized my I need to keep track of these two, the head and the tail. So I initialize my queue function, so I ask to keep track of the head and the tail. Now we're going to start with the empty function. So to check whether if the queue is empty, I'm just going to check if self.head is equal to none, then it's empty. So I can maybe print is empty. I may print is empty, or you can do some other functionality you like. So then I'm going to now call the pick function. So to pick into the queue. Now remember, in a queue, if I want some information from the queue, what the queue will do to me, it will give me the head. It will give me the what? It will give me the head information. So it will not give me this information that has just been put into the queue. No, it it will give me this first information, the head information. So it will be this information here, meaning that I will need to call this, I will need to return myself dot head dot data. So it will return for me that. So remember, in this case, if the head is empty, you may want to write a conditional here to check if the head is empty, so that to prevent some errors, or write a try catch a try except block. Now, what if I want to add information or data into the queue? So to add information into data into the queue, remember now here in the queue we add information to the tail, not to the head. Information is added to the tail. So if I want new information, it's supposed to be added here to the tail. So to add new information onto the tail, I'll first check if the tail is empty. So to do so, to check if the tail is empty, I will say, if self.tail is equal to none. Now, I could first check if the tail is empty, I do nothing, then else I do something. Or what I would do, I would just check if the tail is not equal to none, meaning that if the tail is not empty, what I will do, I will say let myself dot tail.next equal to our new node. So here I'm going to have to make my new node equal to node. My new node will equal to node, then I'm going to pass in the data. So that will be my new node. So myself.tail.next will equal to my new node, right? It will equal to my new node. Equal to my new node. So now the tail has now pointed to the new node. Now we need a new tail. So now the tail will now be the new node. So I'll say myself.tail will equal to the new node. So if myself.tail is equal to the new node, then I will just return the function. What if the tail was empty? So I'll say else. If the tail was empty, I'll just say let myself.tail equal to my new node. Now, what if the head, the head was empty? So I'll check if self.head is equal to none, meaning that if my head is empty, meaning that the new node will equal to the head. Self.head will equal to the node. It will equal to the new node, not the node. It will equal to the new node. Now, what if that is how to add information or new elements or new nodes onto the queue? What if I wanted to remove some information from the queue? Now, if I want to remove data from the queue, the data I remove is the data in the head, not the data in the tail. It's data in the head. So to do so, I will come here on my remove function. Then I will select my data equal to none. So if my data is equal to none, let me first delete this. Let my data equal to none. So now if my data is equal to none, what I will check now, if self.head is not equal to none, what I will do, I will say, meaning that if my head is not equal to none, so let my data equal to self.head.data. Now since I have pulled data from the head, I need to now remove the head node. It means that now my self.head will equal to self.head.next, meaning that my head will now be the node that the head node points to. So that will be self.head. Then after that, I'll have to return. After that, I'll just return my data. So I'll return my data. So that is it. So that's how you would implement a queue. That's how you'd implement a queue. Thank you for watching. If you enjoyed, please leave a like button. And if you want to see more, subscribe to my channel. Thank you so much. So welcome back everyone. Today we are going to talk about how to code a linked list. So how do you code a linked list? So to code a linked list, we can start off with let's create a new file, save it, then we're going to call let me call it linked. Let me call it linked. Am I spelling linked properly? Let me call it linked.py. So after creating my linked list, so to create a linked list, we need the following. We need a node. And now, in fact, before even we go to what a node is, what is a linked list? So let me try to explain what a linked list is. Let me open Paint. I think Paint will be the best to explain what a linked list is. So, we're explaining what a linked list. So a linked list is simply a data structure whereby you can have one node, then you have another node, you have another node in a sequence, and another node. Now these nodes can contain different information in them. So this one could have numbers, this could have a string, this one can have a boolean. They could have different data types. Now the thing in a linked list is that this list points to this one points to this one, and this one points to that one. Now these elements here, this one here is what we call a node. This is also called a node, this is also a node, and this is also a node. So a node, what a node has, it has some data, then it also has a pointer, and this is the pointer. This one here, it's the pointer. So that's what a linked list is. It points to the next node or to the next element in that linked list. You could also have a doubly linked list whereby this node points to this node, and then this node points back to this node, and the same, this one points to this node, and this one points back to this node. This one points to this node, and this one points back to this node, and that would be a doubly linked list. So from my explanation, how do we start off by coding? So we need a node. So to create a node, you can call our class node. I call my class node. Since now I've created a node, and remember we said that a node has to have a way to store data and a way to point to the next node. So what we can do, we can initialize our class. So our class, the node will have to take in the data I want to store in that node, and then that data I'm going to store it in self.data will equal to data. Now the node also has to point to the next. It has to point to the next node. So I'll say self.next will equal to none. So in this case, at the beginning it's pointing to no. It's pointing to no. To no node. So then what I'm going to do, I'm now going to create my class, the class for the linked list. So I'm going to call class linked list. Now my linked list can have many functions. It can have a function to append. So I'm going to say append. So this append will take in the data, and then it will append it onto the linked list. So let me call pass. So what this append function does, let me open here Paint. It comes to my last node after me creating my node. Here it will come to the last node, append it, and make this last node point to it. So this last node will point to it. So if it was a doubly linked list, it will also point back to the last node. So then I will have another function called prepend. Let me call it prepend. Self, then it will take in the data I want to prepend. Then I would have to carry out the operation. But what is prepend? So prepend is here. When you have my head node, so this is my head node. The first node in a linked list is my head node. So this is my head node. To prepend is to put a node before the head node, meaning that this node which you have prepended will become the head node. So this node should be able to point to this node. And remember, the head node does not point to any other previous node. It is the head, it's the first node. So that would be prepending. Then I'm going to create another function, which will be, I'm going to call it delete with value. So if I wanted to delete a node from my linked list, I'll just pass in the value of that node, and then I'll be able to delete it. So let's say delete with value. So what you do, what it will take in, self, then data, then pass. I want to carry out the operation. So this is the basic way how a linked list looks like. But now we need to code a linked list. Now in a linked list, one, we need to keep track of the head node. That's the first node. So to keep track of the head node, we need a head variable that keeps track of the head node. So to do so, we shall first initialize our function. When we initialize our function, let's initialize our function. And our initial function, when we initialize it, we are going to create the variable self.head, which will keep track of the head node. But initially it will have none because there is no head node that we have yet defined. So then now we're going to come to append, adding a node in the list. So now to add the node, what we do, we are going to say, what if the head node is none? That's the first thing. What if the head node is none? So if the head node is none, what we do, we can say if self.head is equal to none, meaning that if there is no head node, meaning that the first data that someone sends into the linked list will be our head node. So we shall say self.head will equal to node, then we shall pass in data. So meaning that the first data that someone sends will be our head node. So after this, we shall just return, meaning that we return the function. The function ends there. Okay. Now what if there was already a head node and a bunch of information? So let's come back here. So let me select the whole of this and first delete it. So what if we had this scenario? We had a node, another node, another node, another node, and then they are all linked to each other. This is linked to this one. The head node is linked to the next node, then the next node is linked to the next node, and then the next node is linked to the next node. And we wanted to append a new node at the end. So what do we know? Initially, the linked list has only access to the head node. We have access. If I delete this, let me put in the arrow here. We have only access to this head node. That's the only node we have access to. Meaning that we need to get access to this node. But how do we get access to this last node? This last node has no pointer, meaning that its self.next is none. So what we shall do, we shall write a while loop, which will be given the head node, right? It will be given the head node. Then the first loop, it will check self.next. Then this self.next will be this node. So it will check if this node's next is not equal to none. If this node is not equal to none, then we shall set our current equal to this node. Then we shall continue the loop until we reach our node where its self.next is equal to none, and then we store that node in a variable which we might have defined. So if it's not making sense, let me code it and you see. So now what we shall do, we shall say our current. So this current is going to keep track of our node as we loop through. So our current will equal to self.head, right? Then we shall say while current.next is not equal to none, while current dot next is not equal to none, we continue looping through. So now let's come back here and see, well, what does current dot next not equal to none mean? Meaning that if I pass in my self dot head node, then it checks its self dot next, it checks the next of the head node, and then if the next of the head node is not equal to none, which it's not, it will continue the loop. Then we shall set our current equal to self dot head dot next. Then it will check again if this one's next is not equal to none. If it's not equal to none, it will continue the loop. It will check again if this one's next is not equal to none until it reaches a node where its next is not equal to none. And it reaches that node where its next is not equal to none, it is going to stop the loop. So it will come here and it will check, current dot next is equal to none. So since it's equal to none, it will stop the loop. And then when it stops the loop, this node here that we have now gotten, which it would be in the current variable, and then we shall set its next equal to the node we want to append onto the linked list. So in simple terms, let's go through the code again. Let's see, this is the one. So our current dot next is not equal to none. So what we shall do, we shall say, as long as our current dot next is not equal to none, we shall say let current dot next, let our current equal to current dot next. Then after we loop until we reach the node where its current dot next is equal to none, what we shall do, we shall just say let the current, that's the node where its current dot next is equal to none, let its dot next equal to our data that we have been told to append. So that's how you append onto a linked list. What if we wanted to prepend? Again, prepending is putting a new node to be the head, meaning that our current head, the new node should point to the current head. So the new node which we are trying to prepend should be the head. So to do so, what we shall say let our new head, let our new head equal to node. So our new head is equal to node when we pass in the data. So we have created our new head node. Then we shall say let our new head node point to, let its next equal to self dot head. So if its next is equal to self dot head, now, but in our linked list here, this self dot head is still the old head. So we need to set it into the new head. So we shall say self dot head equal to new head. So we are done prepending. Now, what if we wanted to delete with value, meaning that we pass in some data and then we delete the node with that data? So what we shall first check, what if our linked list is empty? So just say if self.head, meaning that if there is no head, is equal to none, meaning that there is no head. What we shall do, we shall just return, stop the function and return it. What if the data we want to delete is the data in the head node? We shall just say if self.head.data is equal to the data we are trying to delete. What we shall do, we shall say now, when you're deleting information in a linked list, what you do, if I wanted to delete this information, I just get it and then I get this node. Let's say this node. If I wanted to delete this node, what I would do, I'll just get this node, I remove it out of the equation, then after that I point its previous node to the next node, meaning that I've deleted it. So in this case, if I wanted to delete the head node, what we shall do, we shall say let self.head, meaning that the head, this head node here in the linked list, let that head node equal to head.next. It means that in the linked list we have now forgotten about the head node, meaning that remember in a linked list the only node you have access to is the head node. Then from there you can move where the head node points to another node and the next node points to the next node. So if we change our head node and then we make our new head node to be the next node of the head node, then we have deleted the head node. So now we return the function. What if it was not the head node we wanted to delete? So what we shall say current. So I previously explained how to loop through the nodes. So I was just say let current equal to self dot head. So after our current equal to self dot head, let me change this to self dot head. So after our current equal to self dot head, what we shall do, we shall loop through the nodes. So we shall say while current dot next is not equal to none. We shall say if the current dot next is not equal to none, we shall be looping through all the nodes. What we shall do, we shall say if current dot next dot data is equal to data. Now, why did we say current dot next? Because remember, our current initially in the beginning of the first loop, our current is the head node. But remember here we already accounted for data if there is data in the head node, meaning that the node we need to check is not the head node because we already accounted for it. It's the node that the head node points to, that is the current dot next or the head dot next, which is the same since we said let current equal to self dot head. So we check its data if it's equal to data. If our current dot next is equal to data, what we shall do, we shall say let the current dot next, meaning that the current node we have checked, the current node whose data is equal to the data we want to delete, let its port equal to current dot next dot next. Let it equal to the node that it points to. That's what current dot next means. Then that is it. Then the node will be the node will be what? Deleted. But to make sure that the loop continues, we have to select current equal to current dot next. I think also the same should be done up here. Yeah, for the loop to not be infinite, we shall have to select. We already did let current equal to current dot next. Yeah, we did it. So that's how you would implement a linked list. Thank you for watching. If you enjoyed the video, hit the like button. Thank you so much for watching. Hello everyone and welcome back. Today we are going to be talking about trees. Now what is a tree? A tree is just a simple data structure whereby you have a head node or a parent node, and then this parent node points to other child nodes. Now these child nodes can be many. It can point to this child node, it can say point to this child node, and it can also point to this child node. There also can be another child node here. It can also point, first escape that, and it can also point to this child node. Now it doesn't necessarily have to be too many child nodes that it points to. So usually when we are talking about a binary tree, we talk about, a tree, not a binary tree. Usually when talking about a tree, we talk about a binary tree. So a binary tree is whereby you have a parent node, and then the parent node has two child nodes. Then the child nodes become parents and they have two child nodes, or one child node. But it can only have not more than two. It cannot have not more than two child nodes. So usually when we're talking about a tree, we usually talk about a binary tree. But usually binary trees are usually used in binary search trees. But now how do these binary trees work? Let's imagine we had this tree, right? Let's put here. Let me put another node maybe we wanted to add. Put another node here, and this node maybe should have 11 in it. Let's use another color. Should have 11. Now, the way trees work are like this. If the node you are trying to add is greater, if the node you are trying, if I escape this, let me reduce this to that, escape. Let me come here, then let me highlight it small like this. So if the node which you are trying to add is greater than the parent node, it goes to the right. If it is less than the parent node, it goes to the left. So when it comes that you want to add a new node to the binary tree, we want to add 11, it will come here to the top. It will check 10. Now 10 is greater than 10 is greater than what? It's greater than 11. I mean, 11 is greater than 10. It means that it will go to the right side. Here, 11 is less than 20. It will go to the left side. Then here, 11 is less than 15. It will go to the left side. Now 11 is greater than, 11 is less than 13. So it will also go to the left side. So at the end, this 11 will be on the left side of 13. That is if we are adding it to the binary tree. Now the good advantage of binary trees is that they're fast in searching. So when you're carrying out searches, they are incredibly fast. So now there are two types of binary trees. There can be a balanced and unbalanced. Now a balanced comes by whereby when you add, like if we add 2 as our parent node, it will have 2 child nodes. That will come in the case only when the nodes that you are adding, the first 2 nodes that you add, have to be less than and greater than the parent node. If they are not, you will have this unbalanced case whereby if I have 1 as my parent node, then I add the next node I want to add is 2, it will go here to the left. The next node that I want to add is 3, it will also go here. It will also go here to the right, like that. Meaning that this left side of the binary tree will not have been satisfied. But there are usually algorithms that are inbuilt in most binary search tree modules that take care of this problem. So now, if we are searching through a binary tree, there are 3 ways to search through a binary tree. We can have auto traverse. We can have the in-order traversal. We can have the post-order traversal, and then you can have the pre-order traversal. So now, how does a pre-order traversal work? In the pre-order traversal, we first print B, then we print A, then we print C. So in the pre-order traversal, it will be B, A, then C. Now in the in-order traversal, we shall first print A, then we shall print B, then we shall print C. So you will have the left node first, you print the parent node, then you print the right node. Now in the post-order traversal, we shall first print the left node, the right node, then the parent node. That is how the post-order traversal would work. But now, how do we implement a binary tree? So now we are going to start to implement a binary tree. Now, to understand how to implement a binary tree, you should also understand recursion. If you don't understand recursion, you may not be able to understand how this binary tree I'm going to implement it. And the language of my choice, which I'm going to use to implement this binary tree, is Python. So what you can do, you can open up your favorite text editor. Then, after opening up your favorite text editor, you can save it as, let me say, tree. I'm going to call it trees.py. I'm going to save it. So after saving my trees.py, I'm going to start off with my first class. Now the class which I'm going to define first is the node. So what I'm meaning by the node, I have to define these nodes here. These nodes here, these nodes. I have to define what they are. So let me go back here. So let me go back here. So I'll first define my node. Now I will initialize my node class in it. Initialize my node class in it. It will take in self and then data, because each node has to carry some data. So I will have self.data will equal to data. Again, the node has to point to a left node, so I will have self.left will equal to initial and none. Again, it has to point to a right node. Right will equal to none initially. So that will be my node class. Then I can now define my binary tree. So my binary tree. Now in my binary tree, in this case the way I've decided to implement it, the the binary tree class will be able to keep track of the head. It should be able to keep track of the head. So I'll define myself and then data. So when you make the binary tree class at first, when you like create a new object of it, you need to pass in your head data. So this head data, I will get a variable called head, and then the data which you passed in the binary tree object, I'm going to make it into a node and store it in the head variable. So this binary tree object is going to keep track of the head. But there are many ways you could implement it. You could not keep track of the head, and you would keep track of another thing if you would like. But there are many ways to implement it, as long as you have understood the core ideas behind it. So then I'm going to have my different functions. I'm going to have an insert function, which will help me to insert information. It will help me to insert information into the tree. Then I'm going to have another function, contains. It will check if the tree contains some certain data. So I'm going to say contains self pass. Then I'm going to have another function called print in order. So print in order. Now this function print in order will be able to traverse through the binary tree and print the functions in the predefined traversal, either in order traversal or pre-order traversal or post-order traversal. It does not matter. The core idea will be the same. So I'll say print in order. So in this case, I think I'm going to use the in order traversal to demonstrate this. So print in order. Print in order. So print in order will take in self, then pass. Now I have to go on to define these functions. So let's start with the insert function. So we would like to insert a what? Insert a function. Insert some new data into the binary tree. So what will this insert function receive? To receive data. Then it will receive a node equal to none. Now the reason for this node that it is going to receive, it's going to help me in the recursion. Remember I said the way you implement a binary tree, you need to use recursion to implement it. Now later on you are going to see the use of that node which I've set as equal to none. So initially when I want to insert data, I'll first check if the node is equal to none, meaning that if that node has no node has been passed into the insert function, then it means that I am in the first loop, should I say, my first recursion loop, something like that. So my node will equal to self.head. So I will set my node to equal to self.head. Then I'm going to check if data, right, is less than or equal to node.data, meaning that if the data that I've passed, the data that I've put here, let's example, I have put the data that I have passed, it's checking on this node now. If the data is less than this node, it has to put it to the left. If the data is greater than this node, it has to put it to the right. So that is the basic idea that's the basic idea that I'm going for. So if the data is less than the node.data, what I'm going to check if the node.left is equal to none, meaning that if there is no left node, if the node.data is equal to none, then I'm going to select my node.left equal to node, then I want to pass in my data. Then after that I can just return and end the function. I've already put the data into the tree. Else, what if my node.left is not equal to none? There is a left node. What I'm going to do, I'm going to say self.insert. That's where the recursion comes in. The function is going to call itself. It's going to pass data, and this time the node that it's going to pass is now not the head. The node we shall now be checking will be node.left. So if you understand recursion, you should be able to understand how this is going to work now. we're going to go else if the data is greater than or equal to, if it is greater than or equal to node dot data, it's greater than or equal to node dot data, what we're going to do, we're going to check if the node dot right is equal to none, if the node dot right is equal to none, then my node dot right, meaning that if there is no right node, then I'm going to set my right node to equal to the data that I have passed. Then I'm going to return, meaning that I'm going to end the function or return. Else, if there is a right node, what I'm going to do, the function is going to call itself insert, and I'm going to pass in the data, and then the node that now we are trying to check will now be the right node, node dot right. So that is the end of the insert function. That's how we insert data into the binary tree. So in this case, we have used recursion to do this. Now, what if we want to check if the tree contains some data? So first, we shall pass in the data that we want it to contain, and since now in this case we are going to use recursion, so I'm going to select my node initially equal to none. So first delete this pass, let my node initially equal to none. So now I want to check if my node is equal to none, means that I am in the first recursion, which implies that my node should equal to self.head. Then I'm going to check if my data is equal to node.data, then I'm going to return true, meaning that the data exists. If it is the node, if the data which I want to check that the tree contains is equal to the data of this node, this initial node, which is the head node right now, but in the next cases it will be other nodes, then it means that I just return true that the data exists. Or if my node.left is not equal to none, meaning that if the left node is not equal to none, then I'm going to check if my node.left.data is equal to the data that I've passed, then I'm going to return that the data that I'm checking is there, so I'm going to return true. Then else, what if the data is not on that, is not on the left, that left node? Then what I'm going to do, I'm going to recall, the function is going to call itself self.contains, then I want to pass in my data, and then I'm going to pass in my left node, node.left. Then from there, what if now the left node is not also equal to none? Else if node.right is not equal to none, node.left is not equal to none, then I'm going to check if my node.right.data is equal to data, then I'm going to return that yes, that data exists. Else, if it's not the right node, then what I'm going to do, I'm going to say self.contains, then I'm going to pass in the data, then I'm going to pass in the node. That's called, the function will call itself, and I'm going to pass in the node.right. Now in this case here, we can do a simple modification here. Instead of each recursion we check this node, we check if the data is equal to true. What we are going to do, if the node is equal to none here, then what we are going to do, we are going to check if the data.node is equal to the data, meaning that only in this case we are only checking for the head node, then return true, because here in this case we shall check the data of the left node. So then when we pass in the left node and the function is repeating itself, we don't need to check again if the data of the left node is equal to the data that we want to check. So in this case we can make that small modification there. So that is how you check if the binary tree contains some information. So now we are going to use print in order. Initially, because remember we are doing recursion here, you can pass in a node equal to none. Then we are going to check if the node is equal to none. It means that we are in our initial recursion. So our node will equal to self.head. Self.head. Then we are going to check if our node dot left is not equal to none, meaning that if the left node is not equal to none, what shall we do? We shall just, the function will recall itself. Print in order our node dot left. Then after that, we are going to print our node dot data. So if you're not understanding, I'm going to try to explain this, what this means. Now if our node dot right is not equal to none, what we're going to do, the function is going to recall itself. Then we shall print in order node dot right. We shall pass in that. So now what we're going to do is let's try to explain it. So if, for example, we have our 10. Now the initial code shows that let's see, we're going to the initial code we're going to talk about is this here. If node.left is not equal to none, call yourself. So if the left node, this left node is not equal to none, the function will call itself. Then again it will check. If the left node is not equal to none, then it will come here again. If the left node is not equal to none, then it will come here. Then if the left node is equal to none, so in this case it will reach until the last left node here. So if it reaches the last left node there, meaning that now our left node is actually equal to none, then it will come here to print node.data. So what it will do, it will start, let me see, what it will do, it has reached here the last, and then the left node is equal to none. So what it will start, it will print out 1, then it will print out 3, then it will print out 5, then what, it will print out 1, then it will print out 1, then it will print out 3, then our right node will be calling to print out 4 like that, then it will go backwards until it has printed everything we want. So it will print like going backwards. So in this case, let's say 10, we have 10, then we have 5, let's pick out that small portion, then we have 20. So what it will do, it will check if our left node is, 10 will be passed, which is the head node. It will check if our left node is not equal to none, so it's not equal to none, so it will call itself. Itself will check if the left node is equal to none. It will find out that the left node is equal to none. After finding out the left node is equal to none, then the next line in the code will be executed, and the next line in the code is this print node.data. So when my next line in the node is executed, it will print 5, right? Then after printing 5, it will come back to the previous one. Remember, this one here ended on self-calling this one. Since this one has already been executed, it will come back to this one, and then it will print 10. Then it will check if our right node is not equal to none. It will come back here. Our right node is not equal to none. After checking that our right code is not equal to none, then it will print 20. So that's how it works. That's how usually the binary traversal works. So what you could do this is now an in-order traversal. If you wanted, like, for example, a pre-order traversal, what you do, you would just change the position of this print. You may put the print here, and then this one would come the next down, and this one will come the next down. So, like, for example, our pre-order traversal goes as it will go as head node. It will go as head node left, then right, head left, then right. So then meaning that you would change this and then bring it. You would bring it pretty much here. So it will go head left, then right. In order traversal will be left, then it will be head, then it will be right at the end. That's how you'd implement an in order traversal. If you wanted a what? a post order traversal, then this print function would be put here for a post order traversal. So that's how you implement a binary, usually a binary tree, which is mainly a binary search tree. Thank you for watching. If you enjoyed, you can leave a like on the video and subscribe to the channel if you'd like. Hello everyone, welcome back. So today we're talking about heaps. Now what is a heap? A heap is a data structure. Now there can be two types of heaps. There can be a min heap and a max heap. Now, but what is actually a heap? A heap is that form of data structure whereby you have nodes. It's usually like a tree. But in this case, the top node or the head node has to be less than or greater than. That's for a min heap, meaning that the top nodes or the parent nodes have to be less than their child nodes. That's what a min heap is. The parent node is usually less than the child nodes. Like for example, this is the parent node of 4 and 8. So 2 has to be less than 4 and also it has to be less than 8. That will be a min heap. So the same as now, this is also a parent node. It has children and it has to be less than its children. This is also a parent node. It has to be less than its child. 9 is also a parent node and it has to be less than its child. 15 and 20. That is now what you call a min heap. Now a max heap is whereby the parent node is greater than its children. That's where you have a max heap. So now, how do you implement a heap? Now usually when you're implementing a heap, we could define individual nodes that point to 4 and point to 8, but in that case it will be hectic. In this case we are going to use a list. So how do we use a list? When you're using a list, we shall have the first node here would be at index 0. Then these nodes here in this line would be at index 1 and index 2. These nodes in this line will be at index 3, index 4, index 5, index 6. And these last nodes here will be at index 7, index 8, and index 9. But now, when you put them in a list, they will be like this in a list: 2, 4, 8, 9, 7, 10, 9, 15, 20, 13. And they would be labeled from index 0, 1, 2 until the last index, which is usually a 9 in this case, which we have. But now you would ask the question, when we are now in a list, how do we keep track of the parent and the child? Like, how do we know that? Like, for example, 9, how do we know 9's parents and its what? And its parent and its children? How do we know? How do we keep track of that? So we use usually a simple mathematical formula. If we have an index and we want to find the parent of that index, what we do, we get the index minus 2, then we divide it by 2. If we want to get the left, we have an index of a certain node and we want to get its left node, we get the index times 2, then we add a 1. If we have an index and then we want to get the right, we want to get the right node or the index of the right node, we get the index which we have, we multiply it by 2, then we add 2. That's to get the what? The right node. So that is a simple way what a heap is. Now how do we start by implementing what a heap is? So to implement what a heap is, you can open your text editor and then create a new file. So now what we do, you can open your text editor. So in this case I'm going to implement the heap in Python. So I open my text editor, start a new file, then I can save my file. I want to save my file as heaps.py. So then I'm going to start defining my heap. Now to define my heap, I'm going to call my class, then I'm going to call it heap. Then I'm going to initialize init. Then the init will take in self. Then what I'm going to do, I'm going to check the size of the what? I'm going to make a list. That's my list, which will what? Which will have, not checking the size, sorry for that, but I'm going to make a list which will have my elements in the heap. So I'm going to call it items. Then I'm going to have to define certain functions. So in this case, they are the same way I explained them. So I'm going to just pick them and paste them here. Then I'll explain what they are to save time. So I'm going to define a function. Let me tab this. I'm going to define a function get left child index. So in this function, if I have an index and I want to get the left child of that index, this function will return for me the left child, as I had explained before. This one will return for me the right child. This will return for me the parent child. Then this one is going to check whether it has a left child. This one is going to check whether it has a right child. This one is going to check whether the index has a parent. Then this one here is going to return for me the left child. It's going to return for me the left child. This one is going to return for me the right child. That's if I pass in an index, it will return for me the right child of that index. So if I pass in an index to this function, it is going to return for me the parent of that index which I've passed in. Then I'm going to have a swap function. Now my swap function, I'll pass in two indices which I want to swap. So index 1 and index 2. So I will store my index 1 in this variable index 1, store my index 2 in this variable index 2. Then at the position of index 1, I'll put in index 2. At the position of index 2, I'll put in index 1. So that is the simplicity of these functions. They're going to come in handy later on in the code. So now, I'm going to have to define another function. So this function is going to be called pick. What it does, it will just return for me the first element in the heap, or the smallest element in the heap. That's the first element. So it will take in just take in self. Then I'm going to check if the length of self dot items, meaning that if the length of the list is equal to 0, there is nothing in the list, not 90. If it's equal to 0 and there is nothing in the list, what I should do, I should just print maybe something like empty. Then I just return, meaning that there's nothing in the list. Go to the next line, then I just return. But if it's not empty, then I'll just return myself dot items at position 0. That will be my pick function. Then I'm going to do my poll function. Define poll self. Then I'll pass. So I'm going to explain what the poll function does. So this is what a poll function does. Let's go back here to paint. A poll function will take this first node, our first node in the heap. It will take it away and return it. Then what it will do, it will get this last node in the heap and bring it to the what? To be the top node here in the heap. After bringing this last node to be the top node, then it will move. Then it will what? It will rearrange. It will rearrange the nodes to make sure that the node that is here has to be less than its children. So it will heapify down. So it will heap it down, take it downwards. So if 13 comes here, 13 is greater than its children, so it has to go down. So that's what the heapify downward means. It has to go down. So after taking out this top node, it will bring back the last node in the heap, then it will heapify it down. So now let's define the function. So to define the function, we shall first check if the length, that's the length of the list, is equal to 0. So if the length dot items is equal to 0, so meaning that there are no nodes in the what? In the heap. We shall just print out empty. Then we shall return. Then, what if it's not empty? Our items will equal to self dot items, that's position 0, meaning that we shall get that first node in the heap. Then I'm going to check my self dot items at position 0. I am going to replace it with the last node in the what? The last node in the what? In the heap. So also my self dot items. Then I'm going to take the length of self dot items. Then I'm going to subtract 1. That will get for me the last element in that list, which is the last element, the last node in in the heap. Then since now that element is on the top node, then I want to heapify it. That means I take it down, check, make sure that it is less. Since I'm making a min heap, I want to check and make sure that it is less than its children. So I'll just call myself dot heapify. I'm not yet defining the function, I'll define it later downwards. So I'll call myself dot heapify down. We shall define that function later on. Then I want to return my item. So that is, I want to return my item. That is the poll function. Now I'm going to define the function to add an element or an item onto the heap. So I'm going to say self define add, then self, then item. Then after this, I'm going to call myself dot items dot append. Then I'm going to put item. Then I'm going to call heapify up, meaning that if it is supposed to be less, take it going upwards. So heapify up means heapify. I'll call my heapify up after adding it to be the last element in the list. Then I want to take it upwards and make sure that it has to be less than what? It has to be less than its parents. It should not be greater than its parents. That's why the heapify down, it will rearrange the list until the element the new item that I've added has to be less than its parents. So now let's define our heapify up function. So we shall come here, define heapify up. It will take in self. So to heapify up, I want to first get the index. Now heapify up, it takes the last item we have added on the list. So I need to get the index of the last item we have added on the list. So to get the index of the last item we have added on the list, we shall call index, then we shall call the length of the list, self dot items, then we shall subtract 1, then we shall get the item that is that last item in the list, then we shall call it self dot items, then we shall call it index. Then we are going to now check something. It's quite long. Let me bring it. So this is what we are going to check. While this index, while self dot has, this index has a parent, and the parent, this self dot parent will get for us the value of the parent, and if the parent is greater than the item, then we should do something. Now remember, the parent has to be less than the children. So this item which I've put here is the child. So the parent has to be less than, not greater than. So if this index has a parent and that parent is greater than the item or the child, we don't want that. The parent has to be less than the item. So we have to swap the two. So we shall call the swap function. The swap function we defined earlier. Then the swap function will self.swap. Since we're in class, self.swap. Then the swap function we shall call get parent. We shall get the parent index, pass in the index of the child. Then we shall pass in the index of the child. So it will swap the two. So after swapping the two, now it's going to, my new index which I now want to check will be the index of the parent. So I'll say get parent index, then it will call in index. So now it's going to go, now the parent is now the child. So it will have to make sure now that since the parent is now the child, it's going to get the parent of now the child, which was the parent. Then it's going to make sure that the parent is less than the child. So it will go it will be heapifying down, reorganizing the heap until it is well organized. So that's what heapify up does. That's the simple logic of heapify up. Now we're going to do another function and we're going to call it heapify down. It will take in self. Then heapify down. Heapify down comes usually, we called it from poll. That's when we take the first element in the heap. So now we want to heapify the last element in the heap. We have brought it to be the first element in the heap. Now we want to heapify it down. So our index in this case will equal to 0. Then we're going to say while has left, let's call it self.has left child. While this index has a left child, then my smaller child, so the smaller child is usually the child of the parent. So the smaller child index will equal to get left child index, then I'll pass in my index. Then I'm going to make another if statement here. Let me copy it, and then this will be my if statement. So this should be self, then this should be self, then this should be self. So now what we do, self dot has right child. So we're going to check if this index we have has a right child and this right child is less than the left child. It means that the smaller child is now the right child. So then we shall change our smaller child index to be the right child, index. So we shall get right child index and shall pass in index. Now this has to be self, and also this has to be self. Then after us checking that if statement, we shall come back here, and then we shall get our smaller child. So our smaller child will equal to self dot items smaller self dot items, then we shall pass in the smaller child index to get for us the smaller child. Then our parent of the smaller child will equal to self dot items, then we shall pass in the index we have. Then we are going to now make another analysis. If the parent is less than the smaller child, then it's okay. Since we're having a mean heap, the parent always has to be less than its child. So we just end the loop, we break, meaning everything is okay. But else we swap the two. So we shall swap the index, we shall swap the parent, which is index, that's the parent, and then the smaller child index. Then now our index will be the smaller child index. That will now be our index. The smaller child index will be our index. Then the loop will repeat itself until everything has reorganized. That is what heapify down does. So this is how you can implement a heap. Simply you can implement a heap like this. If you have reached the end of this video and you have not understood, try going back, replaying the video slowly and trying to understand until you get what a heap is and how to implement a heap in Python. Thank you for watching. If you have liked, leave a like and please subscribe to the channel. Thank you. So welcome back everyone. So in this video I'm going to talk about hash tables. Let me use blue. As the title shows, we are going to talk about hash tables. Now, what is a hash table? Most of you know what a hash table is. It's like a dictionary. You pass in a key and a value, and then you store a key value, then you store it in the hash table. But how is this dictionary, which people in Python know it as a dictionary, while in Java it is known as a hash map, or a hash map in Java. But in Python, most people know it as a dictionary. How is it implemented? How can we implement it if we wanted to implement it? So what we do, you make an object, then in that object you pass in a key and a value. So after passing in a key and a value in the object will hash the key, meaning that if you know what hashing is like you pass in a string or a number, and then we get that string, and then we change it into a bunch of codes, which are usually in hexadecimal. We change it into a bunch of codes. So then we hash the key. So then after us hashing the key, we convert that hash into an index, meaning that if the hash was like 100010000567, we convert that 100567 into like into an index of 0, 1, 2, 3. How do we do that? We just find the modulus of the length of the list. So if the length of the hash table is 100, then we find the modulus of the hash of the key. Then if you like after us finding the index and the index returned is like 0, then we use the index we use the index 0 to store the value. Now if we want to retrieve the value, what we do when the person passes to us the key, we just hash the key, convert it into an index, then we can retrieve it from the list. That's simple how to make a hash table. But again, another question comes: what if you land in a situation whereby when you hash the key, you can have like 3 or 2 or 4 keys that when hashed have the same hash? How do you solve that problem? Now sometimes the way to solve that problem, there's one way of solving it, but there are many ways. There are many ways of solving it, not one way. But the best way of doing it, which I like personally, is what we call, let me write it down. The best way, it's called chaining. Let me write it, chaining. Now, what is chaining? Chaining will happen in this case. So in this case, if you are at like index, let's for example, this is our list. So you hash some key and then you store its value at maybe the hash has returned index 0, so you store the value here at like 10. Then when you have like let's say at position 1 of the list, that's position 1, there are numerous values whose keys when hashed point to position 1. What we do, we can make another list here. And now in this other list we have made here at position 1, we can now have a tuple. Now in this tuple we shall store in the key, and then we shall store in the what? We shall store in the value, right? Then we shall store in again the key, then we shall store in the value. So then we can close our list. That will be our position 1. So we have chained these values which have the same index. When their key is hashed, we have chained them into a chain. Now, since we have chained them, when you come to check for the value, and then when you have been passed a key, and then you land in position 1, what you do, you just loop through this list at position 1, and then check if this key, you check for the key which matches the key that you have been given, and then you pass out its value. That's one way of doing it. It's called chaining. So now how do we implement a hash table? So I'm going to use Python to implement a hash table in our case. So to implement a hash table, I can create a new file. I'm going to call it hashes, then I'm going to call it table.py. Then I'm going to start implementing it. So to implement it, I'm going to create my class. I'm going to call it my class, and I'm going to call it hash table. Then I'm going to initialize my class. Initialize my class. So after initializing my class, you have to tell me the size. Now this hash table, you have to predefine the size, because remember the size will help us. The size will help us in what? In turning a hash into an index. So then we shall call our self.size will equal to size. Then we need a list of where we are going to store our items. So we shall call self.items will equal to items. Self.items will not equal to items. Self.items will equal to an empty list, and then we have to predefine the size of that empty list, and the size will be self.size. Then we're going to define our put function. How do we put an element into our hash table? So we're going to define our put. Our put will take in self, then it will take in our key, and then it will take in a value. Then we are going to have to hash the key. So now Python, in our case, has a predefined hash function. It's predefined. It's called hash. Just call it key. But if you are coding it in a language that does not have a predefined hash function, then you have to code your own hash function that will help you to hash our key. So after hashing the key, then we're going to need to turn the hash into an index. We turn the hash into an index, we get the hash, then we find the modulus of the size of the of the list, so self.size. Then after that, we say our self.items, we shall pass in the index, and at that index we shall store in our value. Then we shall define our get function. So to get something, you have to pass in the key. Then if you pass in the key, we shall have to first hash the key. So we hash the key. Then after hashing the key, we make an index from the key. It will be our hash modulus self.size. So after making our index from the key, then we can return our value. So to return our value, we just get the item in the list at that index, which we just converted. So this is how simply you can make a hash table. It's not something big, because since in Python you already have a predefined hash function, that's why our code is looking neat. But if we never had a predefined hash function, we would have to define our hash function. So this is how you make a hash table in Python. But Python already has a hash table already predefined, and that's what usually we call a dictionary. So in Python. So thank you for watching. If you have enjoyed, you could leave a like and subscribe to the channel. Thank you.